Hello and welcome to lecture 13. So, in last lecture we were discussing about the introduction to turbojet engine. We were discussing about the special applications of this turbojet engine, and that's what is attracting the attention again towards the turbojet engine. We were discussing about the ideal and actual gas turbine cycle analysis for the single spool configuration. We have done the parameter calculation for ideal and actual gas turbine cycle. Then we have discussed about the performance parameters for the single spool turbojet engine. Now, in last lecture we were discussing about the numerical. The information that's what is given for say UAV company is they are looking for the pressure ratio of 3, turbine entry temperature to be 1200 Kelvin, air mass flow rate is 15 kg per second, different efficiencies what they have assumed they are 100% for the diffuser, for compressor to be 85%, for combustion chamber 98%, turbine 89%, nozzle 94%, and it says the mechanical efficiency what they have assumed is 85%. There is a drop of pressure which is happening inside the combustion chamber and the tailpipe, they are 3% and 2% respectively. And initial calculation they have done at the sea level where they are having Mach to be 0 with the pressure and temperature as 298 Kelvin and 101.325 kilopascal. The calorific value for the fuel it is given 43,100 kilojoule per kg, and we are asked to suggest them the nozzle area required, nozzle radius, nozzle exit velocity, net thrust, thrust specific fuel consumption and efficiencies of this engine. So, as we have discussed, very first we will be putting our TS diagram for the understanding. So, here in this case it says the efficiency of my diffuser is 100% and my flight condition is say ground condition, my M infinity that is what is 0. So, what is the meaning of that? You can understand my cycle that is what will be starting from point 2. Okay. So, let us try to understand this part, let us try to solve this numerical. So, what all we will be doing is we will be dividing my whole gas turbine cycle analysis on component wise. Say we will be first doing the calculation for the intake, from where we will be calculating our pressure and temperature. Next component we will be calculating is my compressor, the output from say my intake, that is pressure and temperature, that will be the entry condition for my compressor, for which the efficiency and the pressure ratio that is what is given. The next process what we will be considering is our combustion chamber, and for this combustion chamber we are given with the burner efficiency, pressure drop, what is my calorific value, mass flow rate, and the exit condition from the compressor, that will be the entry condition for my combustion chamber. So, we will be calculating what will be my pressure and fuel air ratio. Remember here the temperature at the entry of my turbine or the exit of my combustion chamber, that is what is been assumed by the company. Then we will be doing our calculation for pressure and temperature for the turbine, pressure and temperature at the entry of my tailpipe. Then we will be calculating the parameters for the nozzle. Based on all this information, we will try to calculate the exit velocity from the nozzle as we have discussed. We will be calculating our thrust. Then we will calculate our performance parameters like specific thrust, thrust specific fuel consumption, say our efficiency, thermal efficiency, propulsive efficiency and overall efficiency. Okay, so let us begin. So, very first it says my M infinity, it is 0 because it is a ground condition. So, what we know for actual case, my V infinity, that is what will be equal to 0 meter per second. Now, what we know, my diffuser efficiency, that is what is given by H02s minus H infinity by H02 minus H infinity, and this is what is given, say 100%. Okay. So, we will be doing the calculation for the pressure at the exit of our diffuser, that is what is given by this correlation. We know P02 by P infinity, it is a function of my diffuser efficiency and Mach number. Since my Mach number, that is what is 0, so you can say my exit pressure, that is what is given by 101.325 kilopascal. Okay. Now, for the temperature, we know it is independent of my diffuser efficiency, but it is a function of Mach number. Since my Mach number, that is 0, so we can say my exit temperature, it is 298 Kelvin. So, many times we are making our mistake here in terms of Mach number or maybe in terms of diffuser efficiency. So, it will happen that from here only we will be making the mistake, and later on that will be carried forward, and ultimately we will not be getting what actual numbers we are supposed to get. So, you need to be very careful here what condition is given. So, dedicatedly it is been discussed, we are discussing about the ground condition. Okay. Now, let us take the next component, it is my compressor, which is the station 2 and 3. We can say this is my isentropic process and this is representing my actual process. So, let us take the actual process. It says my compression ratio, it is given, that is 3. My efficiency of the compressor is given 85%, and we have calculated our entry condition, that is P02 and T02, that is the exit of my intake. So, based on the compression ratio, we can calculate what will be the exit pressure from the compressor, and this is coming as 303.975 kilopascal. Okay. Now, in order to calculate the temperature ratio, we know that is a function of my pressure ratio and compressor efficiency. Now, pressure ratio, it is known to us, compressor efficiency, it is given. Here in this case, the adiabatic efficiency straightway is given. So, we will be taking that as 85% here, and if we will be putting this number, say T02 is 298 Kelvin and my pressure ratio is 3, we will be able to get the compressor exit temperature, it is 427.28 Kelvin. I am sure you are getting the same numbers. Okay, you can cross verify the answers. Now, let us move towards the next component, it is my combustion chamber, and for combustion chamber we have 3% loss in pressure, that is what we are calculating here. It says 0.97 into what is my entry pressure. So, this entry pressure, it is 303.975 kilopascal. So, let us put this number, it says my combustion chamber exit pressure is coming 294.856 kilopascal. So, make a habit what all information is given, just take carry forward, otherwise there are chances to make mistake here. Now, in order to calculate the temperature, just think of how do we start with. Okay. So, here in this case what we know, we are having the information about say turbine entry temperature. So, we will be putting our block diagram here, and from this block diagram you can do your mass balance, you can do your energy balance also. So, For the energy balance, what we can write down? It is M infinity into H03 plus MF into CV into burner efficiency. That is what will be M infinity plus MF into H04. And we know from this we can derive the correlation for the fuel air ratio. Okay. Now, Cp for the hot gas, it is given 1156, be careful about that. Cp for cold air, it is 1005. The calorific value here you need to take in terms of joule per kg. Okay. So, all these numbers we are considering in joules per kg, Cp values as well as my calorific value. Otherwise, we have chances to make mistake here. So, it says my fuel air ratio, it is coming 0.023. Okay. Now, once we have done that calculation, let us move towards the next component, that is what is our turbine. It is a process 4 to 5, we know that is our expansion process. Here in this case, my turbine which is used to rotate the compressor only. So, we will be putting our say work balance, it is my compressor work, it is equal to lambda times my turbine work. This lambda, as we have discussed, is my mechanical efficiency. So, we will be putting this in this formulation. It says like lambda into MF into bracket 1 plus F Cp T04 minus T05 equal to MCP delta T0. Okay. So, based on that we can calculate what will be our outlet temperature from the turbine. So, let us put the number. My T04, it is given 1200 Kelvin. My Cp for air is 1005. Temperature values are known to me from the previous calculation. If all together we will be putting, it says my turbine exit temperature is coming 1070.75 Kelvin. Now, in order to calculate my pressure ratio, we need to go with the configuration here. It says our pressure ratio, it is given in terms of my turbine efficiency. So, let us put these numbers. It says my T04 is 1200 Kelvin, T05 is 1070.75, that is what we have calculated, and here my turbine efficiency is 89%. From this we can calculate what will be our expansion ratio, and this is 0.572 P05 by P04. So, be careful when we are writing the correlation. Since my P04 is known to me, that is my turbine entry pressure, we can calculate what will be our exit pressure from the turbine, and that is coming 168.6 kilopascal. Okay. Now, next component what we have is our tailpipe, and for that tailpipe the information is given. So, there will be 2% drop of the pressure, and this 2% drop of the pressure we can get the value of P06, and this P06 it is coming 165.23 kilopascal. And we know this process, we are considering our process to be adiabatic process, and that is the reason why my T05 and T06, that is what will be same. Okay. Now, let us move towards the next component, that is our nozzle. The process is represented from 6 to 9. So, for the nozzle, as we have discussed earlier, very first thing we need to do is to calculate our critical pressure. We need to be very careful here. The nozzle efficiency that is given, it is 94%, and that is the reason my critical pressure ratio correlation, it will be in terms of nozzle efficiency. Now, let us put this number. We know our gamma for hot gas, it is 1.3, and if we will put all these numbers, it says my critical pressure ratio is coming 1.91. Now, we have calculated our P06, that is entry pressure to my turbine. So, we can calculate what will be my critical pressure. So, if we will be calculating that, it says my critical pressure is coming 86.49 kilopascal. Now, look at this number. What we realize, this pressure is very much lower than that of my atmospheric pressure. So, we can say my nozzle is unchoked nozzle, and that is the reason why we are considering our exit pressure as atmospheric pressure, and that is 101.325 kilopascal. So, let us use this correlation in order to calculate what will be the exit temperature from the nozzle. Here we can write down this as P06 by P infinity, that is 165.23 divided by 101.325, and if we calculate that, it says my static temperature at the exit of the nozzle, it is coming 956.49 Kelvin. Now, once we have calculated this exit temperature, we know we need to calculate what will be my exhaust velocity, and this exhaust velocity we have correlation based on my actual cycle. It says it is a function of my nozzle efficiency too, and that is the reason why we will be putting all these numbers. It says the Cp for my hot gas is 1156, nozzle efficiency is 94%, temperatures are known to us, and from that if we calculate, it says my exit velocity is coming as 498.32 meter per second. Okay. Now, once we have calculated that, our target is to calculate what is my thrust, and this thrust equation, it is given by m dot infinity into bracket 1 plus f V9 minus V infinity. Okay. So, here if we consider, we are looking for our area. This area is nothing but my nozzle exit area. This number, it is not known to us, but what we know is my mass flow rate. This mass flow rate, as per our continuity, can say it is given by density into area into velocity. So, my exit mass flow rate will be A9 into rho 9 into V9. So, based on that, we will try to calculate what is our area. Okay. Now, in order to have this density, just realize at the exit my pressure and temperature are different. So, we need to calculate the density based on that particular pressure and that particular temperature. Now, if we will be putting that, it says we are getting our density to be 0.37 kg per meter cube. If these numbers are known to us, we can calculate what will be the area of the nozzle at the exit, and it is coming 0.0832 meter square. Okay. Now, once we have calculated that, we can calculate the radius of the exit, and that is coming 0.163 meter. Okay. So, now for this thrust calculation, we have all the parameters which are known to us. So, let us put these numbers, since my V infinity is 0, and here in this case my P9 equal to P infinity, that is the reason my pressure thrust that is what will be equal to 0. So, be careful about this part. So, if you recall what we mean by unchoked nozzle and choked nozzle, that is what will be making impact here on thrust calculation. So, by mistake, if we are doing our calculation for critical pressure ratio to be wrong, there are chances that we will come up with the wrong number for the thrust. Okay. Now, if we will be putting all these numbers, it says my thrust is coming as 7646.72 Newton. Okay. So, you can imagine this number when we say our pressure ratio is 3, my turbine entry temperature, that is what is 1200. So, if you recall, in last lecture I was showing the information about the small engines and they were also having the thrust in this range. So, you can understand the purpose when I say UAV engine manufacturing company or UAV making company, they are planning for this engine design. So, this range, that is what need to be carefully understood. Okay. We can calculate what will be my fuel flow rate, because I know what is my mass flow rate or air flow rate. Fuel air ratio we have calculated and it says this is coming as mass flow rate of the fuel as 0.345 kg per second. Now, you must have realized what is the reason why we are calculating this mass flow rate of the fuel, because we want to calculate our thrust specific fuel consumption. So, let us do this calculation. It says thrust specific fuel consumption is given by mf divided by T. We have calculated our mf, we have calculated our thrust. So, putting these numbers, it says my thrust specific fuel consumption is coming to be 0.0451 grams per Newton second. Okay. So, sometimes we are making mistakes in terms of this number to be coming 10 to the power minus 3, that is what is coming in terms of kg per Newton second. So, be careful about this formulation. Very next thing, that is what is required is my propulsive efficiency. Now, this propulsive efficiency, it is given by thrust into my flight velocity. If you recall, this is my ground condition where my m infinity is 0. So, here in this case my v infinity will be 0 and that is the reason why my propulsive efficiency will be 0. Okay. Now, we can calculate our thermal efficiency. For this thermal efficiency, here in this case we can say my v infinity term, that is what is coming to be 0. Other than that, all the parameters which are known to us. So, if we will be putting all these numbers, it says my thermal efficiency is coming to be 12.8%. Okay. So, just recognize this number. Now, next what we are looking for is my overall efficiency, and we know this overall efficiency, it is given by propulsive efficiency into thermal efficiency. Since my propulsive efficiency is 0, so overall efficiency will be coming 0. Okay. So, you can understand what all we have done is in terms of calculation of cycle parameters. When I say cycle parameters, means what are my pressure and temperature at the entry as well as at the exit. Based on that, we try to calculate what is our exit velocity from the nozzle, which is very important in order to assess our performance parameters. So, let us look at this. These are the numbers what we are getting. So, net thrust we are getting 7646.72 Newton. My thrust specific fuel consumption is 0.0451 grams per Newton second. My propulsive efficiency is 0%, thermal efficiency is 12.8% and overall efficiency is coming 0%. Okay. Now, this performance parameters, when we are looking at, it says the performance parameters for the jet engine are thrust, thrust specific fuel consumption, my fuel air ratio, propulsive efficiency, thermal efficiency, overall efficiency. And we must realize these all are depending on all these parameters. Which parameters? You can say compression pressure ratio, turbine entry temperature, different efficiencies like diffuser efficiency, compressor efficiency, combustion chamber efficiency, turbine efficiency, nozzle efficiency, what is our flight speed and flight altitude. So, change of any of these parameter that will impact on the performance of the engine. So, let us try to look at what analysis we have done. That condition we say suppose as my design condition. So, we will try to do the parametric study, that is what is very important and that is what need to be done thoroughly. So, let us look at what we will be doing. We will assume our turbine entry temperature to be constant and we will be varying the pressure ratio, and what is the effect of this variation of pressure ratio on performance parameter, that we will be discussing here. So, very first let us look at, this is representing the variation of my pressure ratio and how it is impacting on my thrust. So, my thrust correlation, if we look at here, it says when we are increasing our pressure ratio, my thrust of the engine, that is what is going to be increased. You can realize this part, when I am increasing my pressure ratio, all parameters, cycle parameters which are going to change. That is what will lead to change my V9, and that is the reason why we are having the thrust, that is what is increasing with the increase of my pressure ratio. Other parameter we can say as my specific thrust, and specific thrust we are writing in terms of T divided by my airflow rate. We can say since with increase of my pressure ratio, thrust it is increasing, that means my specific thrust also will be increasing. Okay. The next parameter we are of interest is my thrust specific fuel consumption. Here this is what is representing our design condition, and it says with increase of my pressure ratio, the thrust specific fuel consumption, that is what is going to decrease. So, you need to be very careful here, what is the meaning of that. What we say, my thrust, that is what is increasing with my pressure ratio. Since I am putting my turbine entry temperature to be constant, and that is what will lead to change the fuel requirement, and that is the reason why we are having the reduction of thrust specific fuel consumption with the increase of my pressure ratio when I am considering my turbine entry temperature to be constant. Be careful about that. Now, let us try to look at the parameter called thermal efficiency. This is representing my design condition, and we know my thermal efficiency, it is a function of my thrust, it is a function of my exit velocity, and it says with the increase of my pressure ratio, thermal efficiency, that is what will be increasing. Be careful here, this performance parameter what we are discussing is based on assumption that my turbine entry temperature is constant and we are varying our pressure ratio. Now, let us look at the new scenario where we will be putting our pressure ratio to be constant and we will be changing the turbine entry temperature. So, if we will try to look at, just look at this number, it says by increasing the turbine entry temperature, your thrust generation that will be very high. The reason here is, we can say what we calculate in terms of V9, that is what will be higher, because you will be having very high enthalpy at the entry of my turbine, and that is what will lead to increase my V9. Same way we can say my specific thrust, that is what will be coming to be higher. My next parameter, that is what is say my thrust specific fuel consumption. So, if we compare with the previous chart, here the scenario will be different. What is the scenario? When I say I want to raise my temperature, turbine entry temperature, I need to add more amount of fuel, and that is the reason with increasing my turbine entry temperature, my fuel consumption will be higher. Okay? And this is what will lead to change my thermal efficiency also. Okay? So, just understand the parameter what we are assuming at the initial stage, this is what will be giving the idea of variation of one parameter impacting on the performance, all performance parameters, putting other parameter to be constant. Now, let us look at what is the effect of my mass flow rate, that is what is my entry mass flow rate. We will be putting all parameters to be constant, we only will be varying our mass flow rate. Here in this case, with increase of mass flow rate, my thrust, that is what will be increasing. My thrust specific fuel consumption, what we are calculating, it says that is what will remains constant. And if we look at our thermal efficiency, that also will remains constant. Now, the scenario here is in terms of my nozzle area, that is what is of our interest. So, there are different kind of application people they are looking for this turbojet engine, and where we will be having restriction with the nozzle area. Suppose for some application I am having restriction in terms of nozzle area, then this variation that will be taken care of by changing the nozzle area, by changing the mass flow rate. Okay. Now, let us move towards the composite curve here. This is what is a good representation of this particular engine, where we say we are looking for the important performance parameters like specific thrust and specific fuel consumption. And here it shows this is representing the variation of my pressure, variation of temperature, and the combination of these two, how it will be impacting on specific thrust and specific fuel consumption. Okay. Here somewhere we are having our design point. Now, the scenario is, suppose say you are doing your initial calculation, first cut calculation. Now, this will be giving you the indication what all modifications can be done. So, here if we look at, suppose say I am looking for my specific thrust to be on higher side. So, there are possibility, it says maybe you can increase your turbine entry temperature, or you can increase and you can increase your pressure ratio. Suppose I am looking for my specific fuel consumption to be lower, it says I need to move it say lower turbine entry temperature and higher pressure ratio. So, this is what is very important and need to be understood by all of us, and we will be discussing all our cycles based on these parameters again and again. Say at this moment we are discussing about the single spool turbojet engine. In next week we will be discussing about say two spool turbojet engine. Then we are having turbofan engines, we are having turboprop engines, we are having turbosaft engines, where these plots are very much important for us. Okay. Now, once we are having the idea about the ground condition, the company now they are planning to check their analysis for the cruise condition. What it says, like they want to fly at 7 kilometers, 7,000 meter with the velocity of 500 kilometers per hour. At that height, at that altitude, be careful, my pressure and temperature will be different. How it will be different? It says my ground condition pressure, it is on higher side. When I am moving towards the altitude, it says my pressure will be 41.06 kilopascal and temperature will be 242.7 Kelvin. So, all other parameters they have considered to be same, like compression pressure ratio to be 3, turbine entry temperature to be 1200, mass flow rate to be 15 kg per second, efficiencies are also same, my pressure drop for combustion chamber and tailpipe, that is also same. All parameters they have kept to be same. Now, you need to help them in finding the change in area required, nozzle radius, exit velocity, net thrust, specific fuel consumption, and you can help them in calculation of the efficiency. So, as I discussed earlier, very first thing what all you need to do is you need to plot your TS diagram. Now, just realize what is the change here. Let me give you hint. Okay. Here in this case, since this is what is my flying condition, that means my M infinity will be coming into the picture. When I will be having my flight condition, I need to introduce my intake here. So, this is what will be the change. Now, let us put this as a tutorial. You just try to put your efforts, try to do the calculation. In next lecture, we will be doing the solution for this tutorial, and again we will be discussing about say performance parameters under flying condition. Then we will try to compare the performance on ground condition as well as the cruise condition. So, here we are stopping with. Thank you very much. We will be discussing this numerical in next lecture and we will move forward with the other configurations too. Thank you very much.